Standing waves is going to be the topic of this lesson in my new general physics playlist, which when complete will cover a full year of university algebra-based physics. Now in this lesson we're going to talk about waves on a string that's either fixed at one end or both ends, and then waves, sound waves in a pipe, again that's either open at both ends or only open at one end. My name is Chad, and welcome to Chad's Prep, where my goal is to take the stress out of learning science. Now, if you're new to the channel, we've got comprehensive playlists for general chemistry, organic chemistry, general physics, and high school chemistry. And on chadsprep.com, you'll find premium master courses for the same that include study guides and a ton of practice. You'll also find comprehensive prep courses for the DAT, the MCAT, and the OAT. And we're going to introduce the idea of standing waves with a string that is fixed at one end. And where a string does not move, where there's no displacement of the string, we end up calling that a node. And since it's fixed at one end, like in this case attached to a wall, we'll call that a node. And the other end, we're going to oscillate it. I'm just going to oscillate it once here. I'm just going to give it a quick little jostle. And what that's going to do by oscillating it in an upward direction, that's going to introduce an upward wave, so to speak. And as the string pulls upward, it pulls the next segment of the string upward as well, which then pulls the next one upward, and that's going to make it look like the wave is traveling down the string towards the wall. Now when it gets to the wall, the very end of the string doesn't have any other string to pull upward on, so it's going to attempt to pull upward on the wall, but the wall is immovable. So in the same way, if I try to push this wall, rather than the wall moving that way, I end up moving out off the wall from that equal and opposite force according to Newton's third law. Well, same thing for the string here. As it attempts to pull upward on the wall's going to exert a downward force, and the wall wins because the wall's not moving. And as a result, what we see is an inversion in the wave that's reflected back, and it'll travel back. All right, now, as long as all we're doing is oscillating or jostling this string once, one wave travels to the wall, it becomes inverted and travels back, and that's it. But what if we just keep oscillating this every so often, and we can, make it faster or slower, so on and so forth? Well, it turns out that you're going to be sending multiple waves toward the wall, and then you're going to be having multiple waves reflected back. And depending on how fast you oscillate this and things of this sort, you can get a condition of what's called a standing wave. And it turns out it happens when we hit what's called a resonance frequency, or the condition of resonance is met. So in this case, you're going to end up with regions, not just necessarily the fixed end right there, but regions of the string that are not being displaced whatsoever. And we might end up having some additional nodes. Now again, we're going to have this node always at the end. The question is, are we going to have any additional nodes internal to the string here in this case, in which case we'd call them internal nodes. And it turns out there are multiple of these resonant frequencies, and we have to derive some equations for how we come up with these the corresponding wavelengths and frequencies that correspond to these standing waves, these resonant frequencies. All right, so if we take a look, we started with a wave on a string that's fixed at one end, but we classically are going to begin with equations for a wave on a string that's fixed at both ends. So we got the wave that's fixed at both ends, and by definition, therefore, it's fixed at those ends. They're not going to be experiencing any displacement. That's going to be a node. So it turns out you're going to start with your longest possible wavelength and get progressively shorter. And your longest possible wavelength is going to happen when you don't have any internal nodes. And in this case, we obviously can't, oscillate it from one end or the other. This would be like a string in a guitar where you pluck it instead. And in this case, we might pluck it, and the longest possible wave we could get is one where there's no additional internal nodes, no additional nodes whatsoever. And then the reflected wave would go back. Now we've talked about the nodes. The other thing we want to talk about are what's called the antinodes. And here, the antinode is the point where you get the maximum displacement, which is right in the middle, right here. Okay, now this is one possibility. An additional possibility for this string, if we pluck it just right, again, we're always going to have nodes at the ends, but can we get one additional node? In this case, the nodes tend to be symmetrically distributed, and so could we get a node right in the middle of the string? In this case, if we plucked it just right, we could get that lovely wave right there, and then the reflected wave would pass through the very same node, so it would end up right back at the same place, at a node at both ends. So we're constrained for this particular wavelength, having nodes at the end and a node right in the middle, and it's possible. All right, let's take this one step further, and let's add one additional node. So again, we've got still the nodes at the end. But now, if we want to put two nodes in there, if we want to make them symmetrically distributed, got to kind of divide this string up into thirds. There's 1/3, there's 1/3, there's 1/3. So, and then our wavelength would look just like so, and then the reflected wave would look just like so. And so now we have two internal nodes. We went from 0 internal nodes to 1 internal node to 2 internal nodes. We went from 1 antinode there to 2 antinodes, and now to 3 antinodes. So each successive standing wave is going to have an additional node and an additional antinode as well. Now what we want to do is come up with an equation for the wavelength of each of these waves. And we're going to start with the middle one here because this is the easiest, because we can see that over the length of the string, we complete one full wavelength. And you could just simply say that the wavelength is equal to L, the length of the string. Okay, so if we look at the first one, we haven't actually even completed a full wavelength. So we'd have to keep going. This is the first half of the wavelength and then the second half to finish it off. And so a full wavelength would actually be twice as long as the string, as it turns out. And so lambda would equal 2L. Well, in this last one here, now we've actually completed one full wavelength by the time we've crossed 2/3 of the string, and then we get another half by the time we reach the end and stuff like that. So how long is the wavelength? Well, it's just 2/3 of the string. And so here we'd say that lambda equals 2/3 the length of the string for a full wavelength. Okay. Now we've got to come up with, some equation that we can apply that describes each of these. And it turns out, it may not be intuitive, but it turns out the equation is going to be lambda equals 2L over n, where n is equal to any integer. There's the equation for the wavelength. And it turns out n in this case, for this example, you could look at it as corresponding to the antinodes, or you could just say that the longest wavelength has n equals 1, and then the next one with one additional internal node is n equal 2, and so on and so forth, however you want to remember it. So, but here we've got n equals 1, and if n equals 1, then lambda equals 2L over 1, or just simply 2L. So for the second one, we have so lambda equals 2L over 2, and 2L over 2 is just lambda equals L. For the next one, it'd be lambda equals 2L over 3, which is the same thing as saying lambda equals 2/3 L. For the fourth one, n equals 4, it'd be lambda equals 2L over 4, or lambda equals 1/2 L, so on and so forth. Now it turns out, we talk about this original wavelength here, so as being the longest possible one. Well, we want to look at the corresponding frequencies, and the frequency that corresponds to that longest wavelength is what we call the fundamental frequency, or the first harmonic. Now we want to derive an expression for these frequencies, and you might recall that the velocity of a wave is equal to its frequency times its wavelength. And if you rearrange this and solve for frequency, you'd get velocity over wavelength. Well, in this case, that would be velocity all over the wavelength, which is 2L over n. And dividing by a fraction, you might recall, is multiplying by the reciprocal. And so this would just equal n times v over 2L. And that is the expression we want to derive for this frequency as well. So it's n times v over 2L. And sometimes you'll commonly see this written where we'll say lambda n or frequency n. And it just tells you that these describe a series of wavelengths and a series of frequencies where n is any integer. Okay, so a couple things to look at here when we talk about this frequency. Now, when n equals 1, again, corresponds to the fundamental frequency. And if we kind of look at this just a little bit different, so Fn equals n times v over 2L. So when, again, n equals 1, you get your fundamental frequency. And so your fundamental frequency is just v over 2L. And notice every other additional frequency as possible is just going to be multiplying that fundamental frequency v over 2L by a different integer. Now again, when n equals 1, that's your fundamental frequency or first harmonic. So, and then the additional ones, when n equals 2, that's your second harmonic. When n equals 3, your third harmonic. When n equals 4, your fourth harmonic, so on and so forth. And all of those harmonics are just equal to a multiple of that first harmonic, that fundamental frequency. So again, when n equals 1, the frequency is just v over 2L. And if I told you that the fundamental frequency was 100 hertz, and then I said, well, what's the second harmonic? Well, it'd be 2 times that fundamental frequency, it'd be 200 hertz. What would be the third harmonic? Well, it'd be 3 times that fundamental frequency, it would be 300 hertz. What's the value of the fourth harmonic? Well, it'd be 4 times that fundamental frequency, it'd be 400 hertz, so on and so forth. So all the successive harmonics are just a multiple of that first harmonic, of that first fundamental frequency. Okay, so this is kind of how it works out for a wave on a string that's fixed at both ends. Now we want to go back and take a further look at a string that's fixed at just one end. All right, for a string that is fixed now at just one end, again on that one end you're going to have a node. So, but now we're going to be oscillating it from the other end. And so it's going to experience a point of maximum displacement at that other end by definition, because that's where we're oscillating it from. And so that has to be an antinode. And so we have to say, okay, how can we come up with some standing waves here? So not only does the wave have to start on an antinode and then hit a node, but the reflected wave then have to exit on an antinode as well. And we see that we can indeed do this without introducing any new internal nodes. So your wave coming in hits a node and then reflected right back out. So this is when n equals 1, it turns out. And if we try to come up with an expression for the wavelength is not equal to 2L anymore. So again, if you look back over here, what was fixed at both ends, over the length of the string, we completed a whole half of a wavelength. Well, here it looks like we've only completed like the second half of that half of a wavelength. This is only a fourth of a wavelength. So as a result, if I wanted a full wavelength, I would need something 4 times the length of the string here. And so lambda would equal 4L. Cool, and you might be like, well, hey, we just kind of took that and said, for the fundamental here, that longest wavelength, and we just said divide it by n and life is good. And then that's pretty much what we're going to do, almost. So lambda n here is going to equal 4L over n, and then we can derive the corresponding formula for the frequency. But we run into a problem when we try to draw the next standing wave. If we go to draw the next standing wave, we might be tempted, oh, you just put a node, an internal node, right in the middle of the string. If you put a node right in the middle of the string, there is no way to have a wave going towards the wall and a reflected wave both travel through that node, both start on an antinode, so terminate on a node, and both travel through the internal node. It's impossible. And it turns out there's no corresponding wavelength for n equals 2. When you go to n equals 3, it turns out you can put an internal node 1/3 of the way in, so 2/3 from the wall, and this works. And so you start on an antinode yet again, terminate on a node at the wall, and there's your wave going toward the wall. The reflected wave's inverted, and perfectly goes right back through the node and exits the string, if you will. I say exits. So it ends the other end of the string with an antinode, and it works. But that's for n equals 3. And it turns out for a string that's fixed at one end, not all values of n are possible. Only the odd values of n actually give you a standing wave and a resonant frequency, if you will. So in this case, we have to say that n equals 1, 3, 5. So with the string that was fixed at two ends, any integer value of n. But for a string that's fixed at one end, just the odd values of n are possible. And so when n equals 1, we still call that the fundamental frequency or the first harmonic, but there is no second harmonic. There is no fourth harmonic. There's just a third harmonic and a fifth harmonic and a seventh harmonic, so on and so forth for a string that's only fixed at one end. All right, so if we come up with the equation for the frequency, so it'd be the same kind of a thing, and we'd end up with frequency is equal to nv over 4L, where once again, n has to be one of the odd numbers. So we've derived our equations for frequency and wavelength here for standing waves either on a string that's fixed at both ends or a string that is fixed at one end. But it turns out we use these exact same equations for talking about sound waves in a pipe. And it's a pipe that's either open at both ends or a pipe that's open at one end. And if we kind of look, you can kind of see why it works out this way. So if we have a pipe that's open at both ends versus over here where we have a pipe that's open at one end. And so sound's going to come in. Let's look at the one end first. Sound's going to come into the pipe, so it's going to bounce off the far wall and then reflect back out of the pipe. And where the sound enters and exits, it's always on an antinode. And so we could see that this would work out. So the longest wavelength possible would start at an antinode, terminate on a node at the wall, and then reflect back, so at the other end on an antinode, and that works. So it turns out you end up with exactly analogous situation to like we saw here, so and so on and so forth, where only odd values of n actually result in standing waves. Now what's different with the pipe here though is that, again, where the sound enters the pipe, is going to be an antinode, and where it exits the pipe is going to be an antinode as well. And not all the sound actually exits here. Some of it will be reflected back, and there will be a reflected wave for the standing wave here. But it's the kind of the inverse of what we saw with the string, whereas the string we had nodes at either end. So here we have antinodes at either end. But ultimately, the equations work out exactly the same, where all integer values of n are possible, so that your longest wavelength possible is still going to be double the length of, in this case, your pipe, not your string. So on and so forth, but the same equations apply. And so now we know how to treat either a string that's fixed at both ends or a pipe that's open at both ends. And we know how to treat a string that's fixed at one end or a pipe that's only open at one end. And we know which set of equations to use. And I think we're ready to do some plugging and chugging. All right, for the first question we're going to tackle here, it says, what is the wavelength of the fundamental frequency for a 0.25 meter long string that is fixed at both ends? If the speed of sound in air is 340 meters per second, what is the fundamental frequency? So a couple parts to this question. So in the first part is just what is the wavelength of that fundamental frequency? And we're told the string is a length of 0.25 meters. And if you recall, our fundamental frequency, the corresponding wavelength, spans half a wavelength over that, so that the full wavelength for that longest wavelength would be double the length. Or you could just go over here and say it's 2L over 1 for that fundamental wavelength, or at least the wavelength corresponding to the fundamental frequency, and 2L over 1 is 2L, and 2L here would equal 2 times 0.25 meters, which is going to equal 0.5 meters. Okay, so there's the first half of the question. Second half says if the speed of sound in air is 340 meters per second, what is the fundamental frequency? And so again, here, fundamental frequency is F1, where n equals 1. And again, it's going to equal NV over 2L. That's going to be 1 times the V we're given. It's 340 meters per second, all over 2L. 2 times 0.25 meters. All right, 2 times 0.25 is 0.5, dividing by 0.5, which is a half, dividing by half, same thing as multiplying by 2. And 340 times 2 is 680. And this has units of hertz, or per seconds. If you notice, the meters part would cancel, and it's just per seconds or hertz. Cool, and that's all there is to it. So we were told it was string fixed at both ends, so we knew we were supposed to use this set of equations, not this set of equations. All right, let's take a look at the next one here. Next one says, what is the wavelength of the fundamental frequency for a 0.25 meter long string that is fixed now at one end? If the speed of sound in air is 340 meters per second, what is the fundamental frequency? So it's really the same question, but now dealing with a string that's only fixed at one end. And so we've got to use the other set of equations instead. And this one's not as easy to picture. But again, the key is that for the string that's fixed at both ends, the fundamental wavelength is going to be double the length of the string. Now it's going to be 4 times the length of the string instead. All right, so lambda n equals 4L over n, which in this case is going to be 4 times 0.25 meters all over n equals 1 for the fundamental, which comes out to 1.0 meters. Okay, and then the fundamental wavelength, which is NV over 4L, is going to equal 1, told to use 340 meters per second, all over 4L, which again is 4 times 0.25 meters. 4 times 0.25 is 1, 340 divided by 1 is still just 340, and again, units here are hertz, the meters parts cancel. And so again, same question, just dealing with string fixed at one end instead of 2. And the key is just, again, knowing which set of equations you need to use based on which kind of a string or which kind of a pipe you've got. All right, last one here says the fundamental frequency of a guitar string is 83 hertz. What is the frequency of the third harmonic? And if the speed of sound in air is 340 meters per second, what is the wavelength of the third harmonic? All right, so first off, we're told the fundamental frequency, which is F1, is 83 hertz. And the question is, what is the frequency of the third harmonic? Well, let's go back here. So again, we're dealing with a guitar. A guitar is a string that's fixed at both ends. So it's not super critical, we'll find out, but string is fixed at two ends. And in this case, that means that your frequency is NV over 2L. Well, again, when n equals 1, that's your fundamental frequency, and it's just V over 2L. So the third harmonic is going to happen when we plug in n equals 3 instead. And it's just going to equal the n over 2L, the fundamental frequency, times 3. And so if you realize that, you could just say it's 3 times that 83 hertz. So in this case, 3 times 80 is 240, and 3 times 3 is 9. So it's going to be 249 hertz for that third harmonic. And then finally, the question says, if the speed of sound in air is 340 meters per second, what is the wavelength of the third harmonic? And in this case, I've got a couple different approaches I can take, but I don't actually know the length of the guitar string here. But I do know that for any sound wave, or any wave for that matter, wavelength times frequency equals the speed of the wave. So, and I want that wavelength, so it's going to equal the speed divided by the frequency. We're told the speed of sound in this case is 340 meters per second. We can see that the frequency was 249 hertz, which I'll write as a per second. And we'll let our calculator do the rest of the heavy lifting here, but we should get 1 point something meters for that wavelength here. So 340 divided by 249 equals 1.365. And in this case, I want to round that to 2 sig figs, so 1.4 meters. And that was the wavelength of the third harmonic. So again, 1.4 meters. And that's all there is to it. If you have found this lesson helpful, consider giving it a like. Happy studying.